In large systems, rare slow events are no longer rare. You know, that quote from Google engineers Jeff Dean and Luis Andre Barroso just absolutely nails the brutal reality of distributed architectures. Because when you're operating at serious scale, those weird edge cases you think are never going to happen, yeah, they literally become your everyday emergencies. I mean, you know exactly what I'm talking about. It's that 2 a.m. pager alert for a bug that statistically had a 1 in a million chance of happening. But because your system processes millions of requests a second, that impossible 1 in a million edge case is suddenly happening every single minute.
And this leads us straight into a pretty dangerous misconception that plagues our industry right now. You hear it all the time, right? Oh, just auto-scale the application layer, we'll be fine. But let's be brutally honest here. Horizontal scaling multiplies bad architecture. Throwing a bunch of extra servers at a fundamental design flaw doesn't actually fix the flaw. It just creates a much more expensive, much more spectacular disaster.
Welcome to this explainer, everyone. If you're a senior engineer or an architect tuning in, I am guessing you have lived through this exact pain. If you've ever sat there watching your cloud bill completely double while your system's latency somehow actually got worse, well, you know exactly what we're talking about today. We are on a mission here to debunk some very persistent scaling myths and dive deep into the actual underlying physics of why naive auto-scaling just flat-out fails. We're going to tear down some bad habits, and we're going to rebuild using first principles.
So here is our game plan. 1. The horizontal scaling myth. 2. Bottlenecks entail latency. 3. Why stateful services break. 4. Proper architectural fixes. And 5. Designing for continuous resilience. Let's get right into it.
Section 1. The horizontal scaling myth.
Look, there's a seriously lazy reliance in modern development on auto-scaling right now. We kind of treat it like a band-aid, basically using it as a substitute for true architectural design. To understand why this is such a fatal flaw, just take a look at this number, 30,000. In a contemporary hyperscale environment, let's say Uber's backend, for example, a single user action, like just opening the app and requesting a ride, can traverse 500 discrete microservices and trigger over 30,000 remote procedure calls. 30,000. Why? Well, it's because of microfrontends fanning out, all those cascading network hops, automated retries, the whole shebang. If you horizontally scale an architecture like that without aggressively optimizing that inter-service chatter, you're not improving performance at all. You're just creating a massive combinatorial explosion of failure modes. You are literally just asking thousands of servers to generate millions of completely useless network packets.
Moving on to Section 2. Bottlenecks entail latency.
Okay, we have to shift our focus away from the comforting lies of average response times and look at the unforgiving physics of distributed networks. Take a look at this chart. If you are only looking at your average latency, that nice flat blue line, your system looks perfectly healthy. It looks like it's just humming along. But look at the red line. That is your 99th percentile. Averages hide massive, totally unacceptable 10-second spikes right there at the tail end. And in a system that makes 30,000 calls per request, hitting that P99 tail isn't just bad luck, it is a mathematical certainty. If your architecture ignores off-CPU waiting time, stuff like deep context switching, aggressive garbage collection pauses, or thread lock contention, then scaling out just means you have more machines waiting in the exact same line. You haven't solved the bottlenecks, you've just distributed them.
Section 3. Why stateful services break.
All right, let's address the massive elephant in the room, state. We really have to contrast stateless compute with stateful databases here. Because compute is incredibly easy. You spin up more pods, and boom, it scales wide instantly. But think about what that actually does. It creates a massive concurrent load that slams right into your stateful databases. And suddenly, out of nowhere, you are facing total connection pool exhaustion. The database becomes the ultimate bottleneck. It suffers from lock contention, depleted memory, maxed out IOPS. And keep the CAP theorem in mind here. When a network partition inevitably happens under all this load, you hit some very hard limits. You can optimize for consistency, or you can optimize for availability. But there is no way you can horizontally scale your way out of that fundamental trade-off.
So, the crucial takeaway is how application layer scaling directly destroys the data layer. Let's walk through a classic painful example, the infamous N+1 query problem. Step 1. Your newly heavily scaled out application layer queries 1,000 authors. Step 2. It loops through and makes 1,000 separate queries over the network to fetch their books. Step 3. You sit there and watch your database immediately fall over and die.
Horizontally scaling an application that behaves like this doesn't solve a single thing. It literally acts as a self-inflicted DDoS attack on your own infrastructure.
Which brings us to Section 4, Proper Architectural Fixes.
Okay, enough tearing down bad practices. How do senior engineers actually solve latency and scale in the real world? Well, it starts with a concept called mechanical sympathy. Basically, this means designing software that actually aligns with the physical realities of the hardware it runs on. It's all about maximizing CPU cache efficiency and minimizing contention. See, low latency performance isn't just about writing clean code. It's a systemic discipline. You actually have to understand hardware physics. To put that into perspective, fetching data from main memory takes roughly 100 nanoseconds, right? But fetching that same data from an L1 cache takes 1 nanosecond. If your architecture forces constant round-trip trips to main memory, absolutely no amount of cloud scaling is ever going to save you from that fundamental physical latency.
And this right here brilliantly illustrates what mechanical sympathy looks like in practice. Let's compare a traditional bounded queue with the Lmax disruptor pattern. Traditional queues, they suffer from super high contention because of multiple writers and thread locks. This gives you an exponential J-curve for latency the second you're under heavy load. But the disruptor, it uses a pre-allocated ring buffer and a strict single-writer principle. Because the memory is already pre-allocated, you avoid those nasty garbage collection pauses entirely. Actually, by removing write contention and locks altogether, your latency curve stays completely flat until the memory subsystem is absolutely saturated. That is how you engineer for scale at the hardware level.
Next up, we need resilient asynchronous patterns to avoid distributed transaction locks. Enter the outbox pattern. Save locally, broadcast asynchronously. Think about it. If your microservice needs to save a user's order and notify 5 other external systems, doing that synchronously is a recipe for a completely inconsistent state if even just one of those network hops fails. The outbox pattern fixes this gracefully. You write the state change to your main business database table, and you write the event to a local outbox table in the exact same local transaction. Then, separate decoupled worker process safely tails that log to broadcast the events out. You guarantee eventual consistency, and you do it without dragging down your main operational thread.
But hey, if you're broadcasting asynchronously, you are absolutely going to have network blips, and you are going to need to retry requests. That requires idempotency keys. In a distributed system, when a request times out, you literally have no idea what happened. Did the request fail to process entirely? Or did it process perfectly fine but just fail to send the reply back to you? If a user action fans out to 20 different services, you need absolute, ironclad guarantees that an automatic retry won't accidentally charge a customer's credit card twice or duplicate a massive shipping order. Idempotency is pretty much your only safety net here. And please, never underestimate the sheer power of just removing work entirely. Just one optimized cache hit in a high-speed layer like Redis spares your primary database from CPU time, disk IOPS, and network overhead. By offloading those frequent heavy reads, you massively increase your system's overall throughput without adding a single new database instance. And yeah, I know cache invalidation is famously one of the hardest problems in computer science, but honestly, wrestling with cache invalidation is a much better problem to have than watching your primary database completely melt down during peak traffic.
Finally, Section 5, Designing for Continuous Resilience.
So how do we orchestrate all of these first principles so our system gracefully survives those inevitable partial failures? Because if you don't orchestrate this right, you get the butterfly effect. Look at the terrifying anatomy of a retry storm here. This is straight out of chaos engineering playbooks. A localized client failure happens, that failing dependency triggers immediate retries. And if you don't randomize your retry intervals, a crucial concept known as jitter, every single failing client is going to retry at the exact same millisecond. That creates a massive localized thundering herd. Then clients of clients start to retry. Within seconds, you have exponential traffic growth that completely overloads your already degraded services. A tiny insignificant glitch can take down a fully scaled fleet if you haven't engineered back pressure and jitter into your system.
The reality is, operating a distributed system is fundamentally different from what we used to do in the past. As engineer Gurgly Oros perfectly put it, operating a monolith is a lot like fixing a single car. You build it, and then it just needs some occasional maintenance. But operating a distributed system, that is like running a massive city hospital. It requires constant, active validation. A hospital has triage, it has backup generators, it has isolated wards. Your software needs those exact same things. Load shedding acts as your triage. Failover serves as your backup generators. And architectural bulkheads are your isolated wards. You need black box testing and routine failover drills just to maintain a baseline of health.
So all of this builds into a really actionable checklist for architects. The resiliency playbook moving forward is super clear. First, you must instrument end-to-end P99 latency budgets. Seriously, stop looking at averages. Second, cut your network tax by moving to compact binary formats like gRPC and L4 routing. Third, implement jittered retries and selective hedging to keep that tail latency under control. And most importantly, build bulkheads and load shedding directly into your application. I'm telling you, actively shedding 5% of your traffic to save the other 95% is the ultimate sign of mature engineering. Isolate your failures before you ever hit that auto-scale button.
Which leaves us with this final critical thought to chew on. When you sit down and look at your architecture tomorrow morning, ask yourself honestly, are you actually engineering a resilient, highly performant system using first principles? Or are you just throwing hardware at a bad design and heavily subsidizing your cloud provider in the process? Think about it. Thanks for joining me on this explainer, and I'll catch you next time.